Alright, this is where we left off on lecture 37, and right before this we had talked about how reactions normally do not happen in a single step, that they usually happen in multiple steps, and we call those steps elementary steps, and that you can write a rate law for each elementary step just using the coefficient in front of the reactants as the exponent in the rate law. And so what it's showing you here, we had just looked at and saw that the step 1 rate law matched the overall rate law. And notice it's the slow step. Okay, so important thing is what's at the bottom. The rate of the overall reaction is always equal to the rate of the slowest elementary step. And they have to tell you which step is slow or fast if they're asking you to determine the rate law for the overall reaction. Or they could give you the rate law for the overall reaction and ask you which step is the rate determining step, because you can write the rate law for the elementary step and just, okay, you know, this step matches the overall, therefore this is the rate determining step, aka the slowest step. Okay. Next. Alright. Yep. I've said that already. Okay. Here's another one. So those are kind of the easier problems. This is the one where it's not quite so simple. Okay, so we've got an overall reaction, step 1, step 2, and we've got the rate law for a fast reversible reaction. Okay, so the 1 is like, this is the forward, and then reversible would be the -1. Okay, but then the slow step, the rate determining step, has these two things. The problem is that the NO3 is an intermediate, and we don't know its concentration. We have no control over that. So you cannot have an intermediate in your rate law. So that's some important thing to write down. You cannot have an intermediate in your rate law. You can only have reactants. You could have a catalyst, but you're probably not going to write one that has a catalyst in it because we haven't even gotten to the catalyst yet in this lecture. Okay, so what the heck do we do to get the correct rate law? Okay, what we're actually going to do is we're going to substitute using this. We're going to set the NO times the O2 equal to the NO3 and then plug it in. So that's what we do on the next slide. Da-da! Is this already printed for you guys?
Yeah.
Yes. Okay. So the only thing that I hate about doing these problems is that the rates, I'm like, do they really cancel out like that? But we're just going to assume they do. So substitute in for the concentration of NO3, those two things. Okay. Wait for that thing to get out the way. Dun, 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 dun. There we go. So then, you know, since you've got two NOs, you would change that exponent to just squared. Okay. And then you end up with whatever the rate is. Now, all that K1, K2, K-1, you know in your rate law there's just going to be a K. So if you want to simplify this process, if you've got an intermediate, set the concentration of the intermediate equal to what you got for the reactants, substitute it back in, simplify. Okay. Alright, blah, 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 blah. So, alright. Few things to keep in mind. Okay. Alright, so some terminology. Unimolecular, you know, decomposition reaction. Bimolecular, you've got two particles that come together of your reactants. Termolecular is actually more like trimolecular, but ter goes to 3. Alright, and there's usually not third order reactions because The whole thing is that all three particles have to collide with the correct orientation and with sufficient energy. So remember way back from earlier lectures, they have to collide, they have to be oriented correctly, and they have to have sufficient energy in that orientation of collision. So yeah, that doesn't happen so often. So if you were to make a prediction about these, if you were just comparing, unimolecular to bimolecular to termolecular, you would assume that the termolecular reaction would have the slowest reaction rate of the three, because the likelihood of all three coming together correctly is much, much less than two things coming together or, the decomposition reaction. Does that make sense? What? All right. And then other thing to keep in mind, value of K increases as your temperature increases. Remember, the value of K depends on two things: what reaction's going on and what temperature there is. So if you change the temperature, you're going to change the value of K for that reaction. All right, so I expect to see something like this on the test. All right, so we got two processes. We've got the rate constant, and we've got what kind of elementary reaction it is. So which one's going to have the higher rate under standard conditions? We'll look at the rate constant. Which one's larger, process 1 or process 2? Process 1. So we would expect process 1 to be at a much faster rate. Do y'all have to write that? Yes. Okay. So I'm going to pause in recording while they write this down. Alright, so another one. So we've got two processes. This time you don't have the value of K, but you need to look at the rate law. So what we just looked at a couple of slides ago, with it being, unimolecular, bimolecular, or termolecular. Alright, so process 1, what would you call that? Uni, bi, or ter? Termolecular. And then process 2 would be what? Bimolecular. And what did we just say about those? Which one's going to happen faster? Remember, what's more likely? 3 particles colliding with the correct energy and orientation, or 2 particles colliding correctly? The 2. So we would assume that process 2 is more likely to proceed at the higher rate. Pause while y'all write that down. Alright. Catalysts, finally. Okay, so big thing to remember about catalysts. They provide an alternate pathway for the reaction to happen. And he doesn't say that necessarily, but that's a better way of remembering. Because if you have a catalyst, it's there at the beginning, so it looks like a reactant. It's also there at the end, so it looks like a product. But what it does is, by its presence, it allows the reaction to happen at a faster rate because it provides a pathway with a lower activation energy. Okay. So I would write that down so you see where it says providing a mechanism. In other words, a pathway, a way for this reaction to happen, a different set of elementary steps with a lower activation energy. Okay. So make sure you star that, know that. I'll ask you about that on the test. Okay, so example, we've got what happens to ozone when it is destroyed. So we've got unimolecular chlorine gas plus the ozone. And so we end up with O2 and chlorine monoxide. Well, then chlorine monoxide will react with unimolecular oxygen, giving you O2 and unimolecular chlorine again. Weird. Alright. But if you sum the reaction, chlorine monoxide, do you remember what that was called? It's produced in one step and then consumed in another step. An intermediate. Reaction intermediate. But look at unimolecular chlorine gas. it's a reactant in this step and it's a product in this step. Although it cancels out, that's how you know it's a catalyst. So, again, catalysts are reactant in one step and then product in the last step. An intermediate is produced in one step and then consumed in a later step. And the way we indicate a catalyst, if you remember this way back from Honors Chem, is that we write the formula of it over the arrow. Remember that somewhat? Okay. Alright, so energy profile diagram showing you the difference. So, I think you have a homework question that asks you to do this. You know, they give you the energy profile diagram for the reaction without a catalyst, and then they want you to draw in where what it would be without a catalyst. So you would go in and just draw a new hump lower, because the whole idea is that a catalyst provides a pathway with a lower activation energy. So your hump is not going to be as high. Do y'all have to write any of that? No. Alright. So, some specific examples of catalysts. Sometimes, if you have presence of acid or base, okay, we're going to talk about surface catalysis in a minute. And then enzymes. Enzymes are just biological catalysts. There are lots and lots of reactions in your body that if it weren't for enzymes, they would not happen at a rate that would be sufficient to keep you alive. So enzymes are good. Alright, so there's an example of acid-base catalysis. Okay, but, I mean, you're not going to have to, like, write that out or anything. It's just showing you an example. Okay. There you go. That's some organic chemistry stuff there for you. So, if you're headed that way, get ready to see all that stuff. But anyway, but remember how we did the redox reactions that were in acidic or basic solution? Okay. Same kind of thing. Do y'all have to write that? Okay, it's printed. Good. Alright, so surface catalysis. You know, the reaction they're giving you here is all gases, but them being in the presence of a specific solid, then that allows the reaction in alternate pathway. Because like this, they collide with the surface, alright? Bonds break, new bonds formed, and then they get away from the catalyst, and the catalyst remains unchanged. Is there anything to write on this one? No. Okay. So, blah, 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 migration. It's just showing you the steps of what happens. Enzymes, you know, I mentioned that. It's biological, and I just told you the reason why a second ago. You may remember from biology the lock and key analogy for enzymes, that it's only it has to be the right shape to fit like a key into the lock at the active site. So if for some reason you have some kind of genetic problem that's not producing the right enzymes, then that could have major health consequences for different things. Okay. So, that's it. Yay! We're done.